Hello and welcome to 2008 era YouTube, where it's just some dude in a room that's dimly lit doing a video on something that I'm very interested in. Now, I will be reading off of a script, so if you see my eyes darting away, just know that that's the reason why. The reason why I'm doing this is because there's a lot of information within this video, and I want to make sure that I hit every single topic and I don't get too off script. Just know that I promise I'm not reading off a Wikipedia article, so feel free to go check the Wikipedia page on what I'm talking about later if you want to make sure that I'm not just plagiarizing Wikipedia, which is pretty funny to think about. Now, the topic of discussion today is going to be on green energy, or more specifically on wave power. Now, green energy has been all the rage recently. By now, we have all heard about geothermal, solar, hydroelectric power, all with the goal to try and capture renewable and clean, carbon-neutral energy from a variety of naturally occurring phenomena. Today, I would like to discuss one of the less well-known and utilized ways of capturing clean energy, known as wave power. In truth, wave power is basically just a derivative of wind power, since waves are usually generated from the interaction of wind blowing on the ocean or any source of water. As a disclaimer, there are multiple mechanisms which a wave can be formed from. It just so happens that wind power is the primary driver behind wave production and an easier to discuss concept, helping to keep this video just much more focused. Now, going back to wind-generated waves, there's a question that we need to answer. If wind is the true driver behind wave production, then why not just capture energy from the wind itself? Well, quite simply, waves are much more energy dense. Certain estimates find that on average, the power density of a wave across a meter squared cross-section is going to be 25 times greater than wind traveling at 12 meters per second across the same cross-section. This is due mainly to differences between density in air versus water. It is much more efficient to capture the energy from a wave since we're able to capture more energy in a smaller area. Now let's look at some numbers. The density of air around sea level is usually equal to about 1.3 kilograms per meter cubed at around 15 degrees Celsius. When comparing their respective power equations, the density variable always has a multiplicative effect, making it extremely important. And as we can see, the density of the sea is much greater than the density of air that the wind is created from. We'll look at a more specific power equation a little bit later on in this video, but for now, just know that density is extremely important for power generation. Now, how do we actually capture this energy? Well, to describe one of the ways that we can do this, we need to first understand the physics concept of work, which is defined as force times displacement in any direction. If you've ever laid back in the ocean and felt yourself move up and down, then essentially what happened is that the ocean, using its waves, did work on you, vertically displacing you. Now, utilizing this principle, engineers have discovered a way that they can capture the energy done by the ocean through its work. And how you do it is as follows. You have a floating device on the ocean. You take a really long rod and you attach that rod to a coil of wire, usually copper wire. What you then do is you take that wire and you move it through a column of magnets. What you can also do is take magnets and move them through a column of wire. Now, if you remember, whenever you move coil through magnets, or magnets through coil, an electrical current is induced. And by having an induced electrical current, what's going to happen is free electrons are going to be able to flow freely, be captured by wires, and then sent into a transformer, which can then be utilized, turned into usable electricity that can be sent onto the grid for end use, be it industry or commercial usage. And that's really cool. We're using the ideas of electromagnetism to create electricity that we can actually use from work that's being done to a device. Now, as you may expect, the main driving force here is going to be the amount of displacement that a wave can provide, or in other words, the amplitude of a wave. Remember, the amplitude of the wave is the difference between the crest of a wave, the very top, and whatever the stable ocean value would be. So in this case, this would be your amplitude. Now, what's great is that if you have a greater amount of displacement, then more force will be created per cycle. Now, let's go ahead and kind of go in a different direction and take a look at the anatomy of a wave. Now, when looking on the screen, we can see the anatomy of a wave. In this case, a normal transverse wave, which is how most waves in the ocean travel anyways. What we can first see is that the very top of a wave is known as the crest, while the very bottom is known as the trough. That's pretty easy to understand and know. The big thing that I really want to hit on is the difference between amplitude and wave height. On the internet and other resources, I've seen some people call amplitude the wave height, and refer to the wave height as the amplitude as well. But for the purposes of this video, I just want you to know that amplitude is the difference or displacement between a baseline value and the crest of a wave, while wave height is going to be the difference between the crest of a wave and the trough of the next wave. Or in other words, it's just going to be twice the amplitude. And whenever I refer to amplitude, just know that I'm referring to the amplitude to the crest. So this amplitude right there. And wavelength is also going to be defined as period. And quite simply, the wavelength is the difference between one wave to the other wave, be it through trough to trough or crest to crest. So I just want to go ahead and make sure to make this very clear, because wave height and amplitude is going to come into key importance soon enough. Let's discuss the physics behind what causes a wave to have a greater amplitude, creating more displacement. There are three main factors to consider when determining what the amplitude of a wave will be. The first is going to be the actual speed of the wind itself. A greater speed means that there will be a greater kinetic energy transfer into the ocean. If you remember the kinetic energy formula of 1/2 mv squared, then a faster wind, or velocity, will exponentially increase the amount of energy transferred into the ocean. That's huge. There's an exponential growth factor there. So as you may expect, the wind speed or velocity is going to be very important. The next factor to determine the amplitude of what a wave will be is the duration of time that the wind is blowing. And, this makes sense. The longer a frictional force is applied, the more energy that will be transferred and ultimately utilized. Finally, the fetch, or the area over which the wind is blowing on the ocean, will also lead to a greater transfer of energy, thus increasing amplitude. And, quite simply, this is occurring because there's just more points of contact for the force itself to actually be applied. So there's no bottleneck. Now, let's think about kind of what causes amplitude to change and try and determine where we would want to put one of these floating devices. Because if wave amplitude is the only thing that matters with these devices, then theoretically, you'd want to place one of these devices in a location that has a consistently strong wind over a large patch of area, or over a large fetch. Now, if this were the case, the Southern Ocean with its westerly winds would be optimal. Winds there can reach about speeds of nearly 100 miles per hour pretty consistently, and as we know, speed and velocity of wind is very, very important. But as expected, however, this level of intensity is very unpredictable and unstable, chaotic even, which can lead to a lot of problems in terms of the actual durability of one of these engineered products. So realistically, you'd want to find a location that has waves with a consistent amplitude that allow for a wave machine to capture the maximum amount of energy possible based on its design. So if you go ahead and design a device that is able to capture the maximum of energy in waves that have an amplitude of 15 meters, then you're going to want to make sure that you place that device in an area that has 15-meter high waves on average, right? Now, to find a location with such optimal wave heights and be able to know around which location and parameters to build your device around in the first place, scientists utilize a statistical measure known as significant wave height. Okay? Significant wave height, not amplitude. And what this does is it measures the average of the top 1/3 of all heights measured across all waves in a certain location throughout a certain interval of time. Now, I'm not going to lie, that sentence is extremely confusing, so let's talk through an example of exactly how we could find this significant wave height value. To determine significant wave height, we would first determine the height of every single wave measured within a period of time. What we would do is measure all of the heights, which is again, this to there. Once we do that, what we would do is then plot all of these heights. And then we would split them up into buckets, where based on all the heights, the top 1/3 highest heights will be in the top bucket. The middle 1/3 highest heights will be in the middle bucket. And the bottom bucket will contain the lowest 1/3 of all the heights measured. So the highest bucket would likely be this wave, that one, this one, and the lowest would probably be this one, and that one. Now let's go ahead and plot it into a table. So after it is plotted into a table, what we would then do is find the average of the top 1/3 highest waves measured. And that average that we would get, which I believe comes out to about 26.5 meters, is going to be the significant wave height. Okay? Height. What we could do is then divide this amount by 2 and come up with a significant amplitude value instead. Now, why are we taking the average of the top 1/3 heights? Why are we not just taking a flat average across every single wave that we measured? Well, to understand this, we need to go ahead and take a look at the distribution curve for waves measured over time. So let's do that now. The waves being measured over time, nearly everywhere, follow what is known as a Rayleigh distribution, statistical distribution, where essentially what's happening is that it's skewed to the right, meaning that values that are smaller are going to essentially interrupt the average estimate that we would find, placing the average around right there. And that's not what we want. Plus, those waves are so minor that it really could be negligible, just treated as the ocean being flat anyways. So by basically taking the average of the top 1/3 of the heights that we measured, what we're doing is essentially pulling the average a little bit further to the left to get a more accurate representation of exactly what the significant mean height would be. Now, one thing to notice, of course, is that there are still values to the left. And what we find is that 14% of waves are going to be higher than your significant wave height. 14%. And then around 3 times in a 24-hour period, you are going to see a wave that is twice as high as the significant wave height. And from there, there's a diminishingly small probability that you would see a wave that's going to be anything higher than 2 times the essentially wave height. And this is a great measure because it can allow engineers to know kind of what the environment would look like if they were to place their machine there to capture this energy. They'd be able to design it in such a way that it can most optimally operate at a significant wave height, while also being engineered to be durable enough to withstand a wave that could technically get 2 times as tall as the significant wave height, and maybe even bigger on a diminishing probability. Now, as long as a massive storm doesn't hit, the probability that you actually are going to see a wave that is just massive is going to be very, very unlikely. meaning it's going to be quite safe to place a device in an area that has a significant wave height that you've engineered your device around. Now, we just finished up discussing how the height of a wave is extremely important for devices that utilize the work done by the displacement to create electricity. We also discussed how we can find locations that have a significant wave height that will allow for these machines to extract the full amount of energy in a singular cycle. But of course, there's another factor that we have to discuss, which is how many cycles occur within a given time frame. Because if we just have one massive wave come by, and then we don't have another one for 12 hours, then a machine's not going to create that much electricity. Now, to discuss the importance of this, and to kind of bring everything together that we discussed about wave height, let's go ahead and look at the power equation for a wave, and discuss the multiple variables that can affect how much power a wave can generate. Now, on the screen is the power equation that I was just discussing, with big P equaling the amount of power generated in terms of kilowatts over a wave front. The first thing we should look at is the right side of this equation. Now, as we can see, significant wave height is squared, meaning that's pretty important. If we wanted to find this in terms of amplitude, simply divide by 2. Now, the T is, of course, time, or more specifically, the time it takes for the wave to basically complete one entire cycle, where the longer time it takes for the wavefront to pass through an object, or in this case our device, leads to more power generation. And of course, you multiply these together. One thing to note is that time is not referring to essentially the total power generated over a huge period of time, but rather the power generated throughout one wavelength or period. So if we wanted to essentially find the total amount of power generated over a certain long span of time, be it an hour or a day, we'd essentially have to sum together every single period, or rather the power generated in every single period. You of course can do some calculus in order to discover this. However, I really just want to look at one period. Now let's go to the left side. Now, on the left, you see little p. And little p just stands for the density of water. And then g squared, of course, is going to be acceleration due to gravity, or rather gravity, 9.81 meters per second squared normally. Finally, you're going to divide this by 64 pi. To be honest, I'm not quite sure why you divide by 64 pi. So I'm going to go ahead and trust the people who proved this equation, since they probably have much more mathematical experience than I do. Now, the way to think about this is that this is essentially a force multiplier for this value right there, where really density is the only variable that is going to be changing. So more dense water is going to create more power. And as we know, water is denser than air to begin with, so it's going to also create a lot more power when then compared to air. Now, speaking of wind power, let's go ahead and look at the respective equation for wind power. And it's as follows: 1/2 times density times area times velocity cubed, which is huge. The reason why I think it's interesting to look at wind power is just to kind of discuss again why we say that fetch, duration, and speed of wind is extremely important for wave production. And as we can see, speed is extremely important since it has a cubic effect for power generation. We can also see area in terms of fetch as being important. And then again, if we added a time variable here and basically did some calculus, we could discover the total power generated from wind over some duration of time, which of course is also very important. One thing to note is that the main driving force behind wind power is essentially going to be the velocity. And the main driving force behind water power is going to be the average wave height, as well as density. Now let's go ahead and look at both these equations and figure out, utilizing their most important metrics for power generation, how we could get wind to generate as much power as waves. On the screen is my Excel workbook where I have the two respective equations on either side. One thing to note is that for every value that I will not be manipulating, I took a constant based on averages. Down here on the left is going to be the average wind speed or velocity in terms of meter per second found throughout all the wind turbines. And down here it's going to show you how many times more powerful water power is going to be. Now let's go ahead and place everything about average for all of these. What we can see is that if you have a period of 2 seconds and you have everything averaged out for wind, then water power is going to be about 9 times more powerful than wind power. Now let's go ahead and crank up wind velocity to nearly the upper bound of wind velocity that is seen. Even if we do that, and we push all these numbers about as high as they can go, you're still going to have water power that is about 2 times more powerful when compared to wind. But let's say that we can pump these numbers up even higher. So we have a velocity of 15, which is pretty unlikely, an area of 200. Then wow, it's generating a lot more power, almost 2 times as much. But if we change the period time to something like 4, oh no, it's catching up, 5, it's already caught up. And time can easily be manipulated. And that's not even getting into how we can go ahead and have a maybe higher significant wave height in terms of meters. And maybe the water in the ocean is going to be slightly denser. As we can see, water power is just a much better source of energy and electricity production than wind power. Even if there are small changes in the certain variables in terms of water power, those small changes are going to have an astronomical effect on this equation and power output as compared to massive changes within wind power. Because remember, the upper bound for speed or velocity is going to be around 10 meters per second squared, or meters per second. And then area, well, that it can be manipulated and changed, right? And one thing to note about density is that since you're going to be higher up in the air, since these turbines are higher, there's going to be less dense air as you go up and up. So really, the best bet with wind power is to find a way to essentially have greater kind of windswept area from the blades, which of course has its own problems. In order to make those bigger, you have to have a more stable base, right? Which means you have to either find a way to reinforce these wind power stations or find a way to shorten them so they don't tip over. But say we can fix up area. Boom. So if we can somehow discover a way to really boost up that windswept area, then maybe, just maybe, wind power can have a chance. Or maybe not. Now, there are a few other ways that we can utilize machines that we place in water to capture energy to create electricity. And the other big way is really about spinning a turbine. To start, what you can do is have a device that sits in the water at some point, and then what happens is water is going to hit the device, come in, and then spin a turbine that's in the center. Another device that you can have is going to be essentially right by the side of a beach, where what happens is water will basically rush into this device sitting like this with an opening, and it will fall, spinning a turbine before feeding back out into the ocean. And that really utilizes tidal power more so than wave power, because as the tide comes up, water will pour in and spin a turbine. Now, I have issue when it comes to these type of turbine machines, mainly because a lot of power is going to be lost whenever a wave hits the side of one of these machines. On top of that, they're also just a really big eyesore being right there by the beach, not looking too complex or even being too complex. I really think that using magnetism to capture electricity is going to be the future of wave power. It is easily the most efficient and effective way at generating electricity from wave power. That's not to discredit these turbine-style machines, because obviously they're being utilized. All we have to do is look at hydroelectric dams, which use the same principle of having water fall very high and having that kinetic energy spin a turbine. And if we're already doing that, why even bother putting one of those machines in the water to capture a measly amount of power and energy from water just falling into it? Anyways, thank you all for listening. I am by no means an expert when it comes to physics or water science or anything like that. But I did a lot of research in this video because I'm truly passionate about wave power, and I think that it can be the future of sustainable green energy. Thank you again.